In the beginning, there was silence, then something changed. Not sound, not light, but the trembling birth of both in an instant smaller than imagination. Existence unfolded from nothing, leaving behind no witness, no reason, only aftermath. Across billions of years, humanity would try to name that aftermath. They would build mirrors of metal and glass and lift them toward the darkness, hoping to catch a reflection of their origin. Each discovery drew back another veil, yet what lay beneath was never what they expected. Galaxies drift where gravity should bind them. Space stretches itself wider every moment, faster than before, obeying no known law. Particles flicker into being only to vanish between observations, as if existence itself were uncertain of its own form. The universe, they learned, is mostly emptiness, a fragile web of matter floating in oceans of invisible energy that no one can see or touch or define. For every equation that promised clarity, the cosmos replied with contradiction. The speed of light, once the ultimate boundary, bends in the warped corridors of space-time. The vacuum, thought to be void, hums with restless energy that shapes the motion of galaxies. Even time, that steady river, ripples and distorts, slowed by gravity, stretched by expansion, hinting that it may not be what it seems. Now, at the edge of comprehension, science stands in quiet awe, for the more we measure, the less we understand. The cosmos behaves not like a machine, but a dream of vast and indifferent consciousness, whose logic escapes the language of numbers. And so the story begins, with a confession whispered through the stars. The universe refuses to explain itself. Subscribe, and let curiosity keep you awake. Through every question, the universe refuses to answer. In the long memory of science, there was once a quiet certainty, a belief that the universe could be measured, predicted, and explained. It began in the 17th century, beneath the falling of an apple. From that simple descent, Isaac Newton carved order from chaos. Gravity, he realized, was not divine whim, but law. Planets circled their stars with the obedience of geometry. The heavens, once ruled by angels and mystery, were suddenly ruled by mathematics. This was the first dream of a rational cosmos, a universe built not on faith, but on reason. For nearly 2 centuries it held true. From the motions of comets to the tides of the sea, every rhythm of nature bowed before the clarity of Newton's laws. The cosmos seemed mechanical, perfect, predictable, a celestial clock ticking in the silence of eternity. But even the most beautiful machines, when wound too tightly, begin to show their flaws. At the dawn of the 20th century, that clock began to tremble. Mercury, the restless planet nearest the sun, drifted from its predicted orbit by a margin too small to ignore, yet too precise to explain. Light itself, the most familiar of things, behaved as both particle and wave, defying the neat boundaries of classical thought. Somewhere beneath Newton's clockwork sky, the universe was whispering that it was not a machine at all. Then came Einstein. In 1915, in a small office cluttered with papers and doubts, Albert Einstein proposed a new architecture for the cosmos, one not built on invisible forces, but on the shape of space and the flow of time. His theory of general relativity transformed gravity from a pulling hand into a bending of reality itself. Space told matter how to move, matter told space how to curve. The universe became flexible, dynamic, alive. Einstein's equations were not merely correct, they were sublime. They predicted the bending of starlight by gravity, the slow dance of Mercury, and even the expansion of the entire universe. For the first time, humanity's equations reached cosmic scale. The rational dreams seemed reborn, stronger than ever. Yet with every triumph, something unsettling lingered. The equations predicted an unstable cosmos, one that should either expand or collapse. Einstein, believing in a steady, eternal universe, adjusted them with a mathematical patch, the cosmological constant. It was a term of convenience, a stabilizing trick. But in doing so, he unknowingly foreshadowed one of the deepest mysteries in science. When Edwin Hubble raised his telescope atop Mount Wilson in 1929, he found that galaxies were not static at all. They were fleeing, every one of them, their light stretched red by motion. The universe was expanding, just as Einstein's unedited equations had implied. The constant, once added to preserve stillness, was discarded in embarrassment. Einstein called it his greatest mistake, but it would not remain so for long. the rational dream evolved again. Now, science sought to explain not a fixed cosmos, but a living one, born in an instant of unimaginable density and heat. The Big Bang became the grand narrative of creation, its afterglow still faintly visible as the cosmic microwave background. Every atom, every star, every human thought was born from that first flash. It was a story of elegance, a universe comprehensible from its first moment to its latest breath. Yet even here, reason would meet its limit. In the 1930s, a young astronomer named Fritz Zwicky peered into the Coma cluster of galaxies and saw a problem. The galaxies moved too fast to be held together by visible matter. By Newton's laws, they should have drifted apart long ago. To account for their stability, Zwicky proposed something radical, that most of the mass in the cluster was invisible. He called it dunkle materia, dark matter. No one believed him. Decades passed. Telescopes grew sharper, computers faster. Yet the anomaly remained. Galaxies rotated as if pulled by unseen hands. Stars at their outer edges spun far too quickly. The math refused to balance. Eventually, what Zwicky saw became undeniable. Most of the matter in the universe was missing. Invisible, untouchable, but undeniably there through its gravitational fingerprints. It was a strange kind of discovery, one that solved a problem by inventing a deeper one. By the end of the 20th century, physics had constructed its twin towers, Einstein's relativity for the large and quantum mechanics for the small. Together they explained almost everything, from the birth of stars to the decay of atoms. Humanity could now predict eclipses centuries ahead, detect ripples in space-time, and even simulate the first seconds of creation. It was the golden age of understanding. The rational cosmos for a moment felt whole again. Then came the shock. In 1998, two teams of astronomers, the Supernova Cosmology Project and the High-Z Supernova Search Team, observed distant exploding stars to measure how the expansion of the universe was changing over time. According to theory, it should have been slowing down, its energy spent against the pull of gravity. Instead, the data revealed the unthinkable. The universe was not slowing down. It was accelerating. Something unseen was driving galaxies apart with growing speed, defying the gravity of all known matter. They called it dark energy. The term carried an air of confidence, but it was, in truth, an admission of ignorance. No one knew what dark energy was, only that it existed, permeating every cubic meter of space, dictating the fate of the cosmos. Roughly 68% of the universe's total energy lay within this nameless force. Dark matter accounted for another 27%. Ordinary matter, everything we can see, touch, or imagine, was just 5%. In the age of reason, 95% of the universe had gone missing. The rational dream cracked again. The cosmos had turned inside out. A place governed not by light, but by shadow. And so, science stood before a strange irony. Every new discovery, every expansion of knowledge, revealed a deeper void of unknowing. The equations that had once mapped the stars now faltered at the boundaries of comprehension. Quantum mechanics and relativity, when brought together, refused to cooperate. Gravity would not be quantized. Space, when measured too closely, dissolved into uncertainty. The universe no longer resembled a machine, but a paradox. Still, the dream persisted. Physicists searched for unification, for a theory of everything. String theory offered dimensions beyond the visible, vibrating threads of energy weaving reality together. The mathematics was beautiful, almost musical, yet it remained untested, speculative, a theory that explained everything, but proved nothing. The deeper science reached, the more elusive truth became. The cosmos, once imagined as a rational cathedral, now resembled a labyrinth, intricate, magnificent, but without a clear exit. Every turn led to another question. Every solved equation opened another void. Even the constants of nature, once thought sacred, began to show instability. Fine-tuning problems haunted cosmology. Why was the universe's expansion rate so precise? Why did physical laws seem perfectly calibrated for life? A fraction of change, and existence itself would have never formed. Some scientists saw coincidence. Others saw design. Many saw only mystery. Even Einstein's discarded cosmological constant returned, no longer a mistake, but a clue. The same term he once invented to hold the universe still now described the invisible pressure driving it apart. The The constant was no longer an embarrassment, it was destiny. And yet, its true nature remained hidden. The rational cosmos had come full circle, from order to chaos, and back to an illusion of order. Behind every law lies another question. Behind every constant, a trembling uncertainty. The universe, it seems, has structure, but not logic. Patterns, but no purpose. Equations that describe, but do not explain. Perhaps that is the quiet lesson of the 20th century's scientific revolution. That the universe allows comprehension only in fragments, never in totality. In the end, the dream of reason was not destroyed, but humbled. Newton's apple still falls, Einstein's light still bends, the galaxies still spin, but the meaning of it all grows fainter with distance. What once seemed inevitable now feels improbable. What once seemed eternal now seems fragile. For if 95% of the universe remains invisible, unseen, unknown, untouched, then reason itself may be only a flicker within a much larger darkness. And in that darkness, science no longer finds certainty, but something far more human, wonder. The rational cosmos was never a lie. It was a mirror, reflecting not the mind of the universe, but the yearning of those who sought to understand it. A dream that began with an apple, reached for the stars, and discovered that the stars were mostly missing. The dream of reason did not fail because it was wrong. It failed because it was too small for the truth it tried to hold. And beyond that failure lies the next chapter of the human story. Not the end of understanding, but the beginning of awe. It began with light, ancient, delicate, and dying. Across the black canvas of space, photons born from exploding stars had traveled for billions of years to tell a story. Their journey began long before Earth existed, long before the sun's first breath of fusion. By the time they reached the mirrors of modern telescopes, they carried with them the memory of a younger universe. It was 1998. Two rival teams, the Supernova Cosmology Project and the High-Z Supernova Search Team, set their sights on type Ia supernovae, the universe's standard candles. These cosmic detonations, caused by white dwarfs collapsing under stolen mass, burned with such uniform brilliance that they could be used to measure the expansion of space itself. The team's goal was simple in theory: to chart how the universe's expansion had changed over time, to trace the slowing rhythm of a cosmos long past its violent youth. But what they found was something else entirely. The supernova were too dim, not by much, but enough to matter. Light that should have reached us, brighter, closer, stronger, was weaker than prediction. This faintness carried a silent implication. The galaxies containing those supernovae were farther away than they should have been. Somehow the expansion of the universe had not been slowing down under the pull of gravity. It was speeding up. At first it seemed like error, a calibration mistake, a misjudgment in distance or dust or starlight. But more data came from Chilean observatories in the Atacama Desert, from Keck in Hawaii, from satellites orbiting high above the atmosphere. Everywhere, the same whisper emerged: acceleration. The cosmos was not coasting gently outward. It was racing away with increasing urgency, as if driven by an invisible hand. Astronomy, once grounded in elegance and order, suddenly found itself adrift. The idea violated every expectation of gravity, every assumption of cosmic destiny. Since the days of Einstein, physicists had believed the expansion of space would eventually slow. Gravity, universal and patient, was expected to pull matter back together, perhaps enough to halt expansion entirely, or even to reverse it in a final cosmic collapse. The universe, they thought, might one day return to where it began. But now, the universe had defied them. It was not falling inward, it was running away. To name the unnameable, scientists gave it a label: dark energy. The term was less a definition than a placeholder, a quiet confession that they did not know. What they did know was that whatever this force was, it dominated everything. By combining the supernova data with cosmic background radiation and galaxy surveys, cosmologists determined that roughly 68% of the universe's total energy was tied to this unseen pressure driving expansion. Matter, both visible and dark, was merely the remainder, dragged along like dust in a rising wind. In a single revelation, the cosmic map was redrawn. Humanity discovered that most of reality was invisible. Not just hidden from sight, but beyond comprehension. dark energy was not a discovery of something found. It was a discovery of something missing. The physics that once held the universe together had lost its anchor. Einstein's equations, which had described gravity with near-perfect precision for a century, now seemed incomplete. Ironically, Einstein himself had once inserted a mysterious term, the cosmological constant, into those equations to keep the universe static. When Hubble later proved that space was expanding, Einstein abandoned it, calling it his greatest blunder. But now, decades after his death, that same blunder had returned, not as a mistake, but as prophecy. The cosmological constant fit the data almost perfectly if reimagined not as a stabilizer, but as a kind of repulsive energy embedded in the vacuum of space itself. Vacuum energy, a haunting idea. Quantum field theory had already hinted that even in absolute emptiness, the void seethes with fluctuation. Virtual particles blink into and out of existence constantly, a ghostly dance that never stops. To the quantum world, emptiness is not absence. It is restless possibility. If these fluctuations carry energy, as theory suggests, then space itself should possess a constant energy density. And energy, through Einstein's equation, curves spacetime. But when physicists tried to calculate the value of this vacuum energy, the result was catastrophic. The quantum prediction overshot the observed value of dark energy by 120 orders of magnitude, the largest mismatch between theory and observation in the history of science. It was not merely wrong, it was absurd. Something fundamental was missing from our understanding. Some scientists proposed that dark energy might not be a constant at all, but a dynamic field, a quintessence that changes over time, its strength rising and fading across cosmic eras. Others imagined that our perception of gravity might be flawed, that perhaps gravity itself leaks across unseen dimensions, weakening its pull on large scales. Still others turned to the multiverse, suggesting that what we observe is only one bubble in a vast ocean of universes, each with its own laws and constants. In this vast landscape, the value of dark energy could vary endlessly, and we, by chance or necessity, exist in one of the rare universes where the numbers allow galaxies, stars, and life to form before expansion tears them apart. It was a beautiful, terrifying possibility. That meaning might be statistical and existence accidental, but for now, dark energy remained silent. Telescopes watched the heavens in disbelief. The Hubble Space Telescope traced the faint light of distant galaxies, their recessional speeds climbing beyond logic. The Chandra X-ray Observatory peered into clusters of galaxies, where empty space seemed to outweigh matter itself. On mountaintops in Chile, the Dark Energy Survey mapped the subtle distortions of light, gravitational lensing caused by the curvature of space, searching for any sign that the cosmic acceleration might vary from place to place. Each new observation deepened the mystery. Every test confirmed what seemed impossible. The acceleration was real, steady, and universal. In 2011, the Nobel Prize in Physics was awarded to the astronomers who first measured it, a bittersweet honor, for their discovery had not clarified the universe, but unmade it. For centuries, cosmology had been a story of progress, of order wrestled from chaos. But now, the very notion of order was in question. The universe was expanding into meaninglessness. If acceleration continued indefinitely, galaxies would drift so far apart that their light would no longer reach one another. The night sky, billions of years from now, would grow empty. Future civilizations might see only their own galaxy, unaware that others had ever existed. In time, even starlight would fade, leaving only the faint radiation of a universe stretched cold and thin. The heat death of everything, and yet, the deeper question lay not in the distant future but in the present. Why now? If dark energy had always existed, its effects would have dominated the cosmos from the beginning, preventing galaxies from forming. If it emerged only recently, what triggered it? Why, after billions of years, did the universe choose this moment to accelerate? It was as if the cosmos had reached an invisible threshold, a tipping point where gravity's patient pull was finally overcome by something far stranger, a pressure not of matter, but of the void itself. Some cosmologists began to wonder if this acceleration might not be a permanent state at all, but a phase, a prelude to something more complex. Perhaps dark energy could decay, shift, or reverse, transforming the universe's destiny yet again. Others proposed a darker scenario, that the acceleration could increase without limit. In that future, called the Big Rip, galaxies, stars, planets, and eventually atoms themselves would be torn apart as space expanded faster than light could travel. No theory could yet say which fate awaited us. Only observation, quiet, relentless, could guide the way, and so, in deserts, mountains, and orbit, humanity built new eyes. The Euclid mission, launched by the European Space Agency, now scans billions of galaxies, mapping their shapes and distances with unprecedented precision. NASA's Nancy Grace Roman Space Telescope, still to come, will join the quest, searching for the fingerprints of dark energy in the geometry of space. Each mirror, each detector, each lens serves the same silent hope that somewhere, hidden within the pattern of expansion, lies a clue, a key to why the universe began to accelerate and what it means. But the answer remains distant. For all its data, for all its precision, cosmology still faces the same haunting truth it met in 1998. Most of the universe is missing. Not missing in the way a misplaced object is missing, but missing in essence, unknowable, unseen, untouchable. The visible cosmos, the stars and galaxies that fill the night sky, are the exception, not the rule. They are the foam atop a vast, invisible ocean. Dark energy does not reveal itself in light, nor leave a trace for instruments to capture. It acts only through emptiness, shaping the destiny of everything by pushing everything apart. And so, 25 years after its discovery, science finds itself still standing at the edge of understanding, watching a universe that behaves as though it wishes to vanish. Perhaps, some whisper, the acceleration is not just expansion, but evolution, that the universe itself is transforming, moving toward a state beyond our comprehension. Or perhaps it is entropy at its grandest scale, the inevitable unwinding of all structure, the fading heartbeat of creation itself. Either way, the night sky no longer tells a simple story of birth and decay. It tells a story of loss, of something vast slipping beyond the reach of reason. When the teams of 1998 announced their findings, few grasped the enormity of what they had uncovered. They had not merely measured a new phenomenon, they had rewritten the fate of the cosmos. They had revealed that everything humanity can ever see or touch is a small island in a sea of the unknown. That, for all our equations and instruments, the universe remains an unfinished thought. And that on the day the universe went missing, science discovered not how much it knew, but how little it ever could. The deeper humanity looked into the workings of the cosmos, the more the numbers began to rebel. What once appeared as a seamless fabric of reason, woven by Einstein's smooth geometry and quantum theory's invisible dance, began to unravel thread by thread. The great project of unifying the large and the small, gravity and quantum, order and uncertainty, met not with clarity but collapse. When physicists tried to calculate the energy of empty space, the quantum vacuum that should shimmer with unseen fluctuations, they were met with a result so catastrophic it seemed to mock the very idea of understanding, a trillion times stronger than what the universe allows, a number so absurd it eclipses the meaning of numbers themselves. It was as if the cosmos were screaming a secret that mathematics could not translate. This mismatch, known as the vacuum catastrophe, stands as one of the deepest cracks in the foundation of physics. General relativity, Einstein's grand vision of curved spacetime, had explained gravity with astonishing precision. It told how stars bend light, how black holes form, how time itself stretches and slows. But when physicists tried to let quantum mechanics, the theory of the smallest things, speak the same language, the universe disintegrated into nonsense. Relativity paints space as continuous, smooth, like an endless fabric of silk. Quantum mechanics says that fabric isn't fabric at all. It's frothing, jittering, and alive with uncertainty. Between them lies a chasm so vast that it seems almost metaphysical. Gravity, the oldest and most familiar force, refuses to join its siblings. Electromagnetism, the weak and strong nuclear forces, all have bowed to quantum law. But gravity stands apart, stubborn and aloof, whispering in a dialect the quantum world cannot understand. When equations are pushed to their limits, infinities appear, unphysical, infinite curvatures of space, infinite densities of energy, infinite absurdities. And in those infinities lies the silence of a universe that will not explain itself. Physicists have tried to reconcile the rift with the language of string theory, a proposal that says all particles are but tiny vibrating loops, their frequencies forming the symphony of matter. In its equations, gravity emerges naturally, woven from the same strings that sing the electron and the photon into existence. But string theory requires dimensions, not 3, not 4, but perhaps 10 or 11, curled into spaces too small to perceive. These extra dimensions might explain why gravity feels weak, why it slips through matter like wind through leaves. Or perhaps they are the mathematical shadows of a universe too complex for human intuition. Still, the deeper they dig, the stranger it becomes. Every attempt to quantify vacuum energy, the so-called cosmological constant, yields madness. Quantum physics predicts an energy density so immense that space should have exploded into oblivion. Instead, what we observe is eerily small, but not zero. Just enough to make the universe expand. Just enough to tear galaxies apart. Just enough to exist, and no more. It is a balance so delicate that many physicists have called it fine-tuning of the highest order, as if the constants of nature have been arranged with impossible precision, not by design but by some cosmic coincidence beyond reason. The cosmological constant, once introduced by Einstein as a mathematical patch to keep the universe static, has become the heartbeat of dark energy, the invisible pressure accelerating everything outward. He once called it his greatest blunder, but decades later, it re-emerged as one of the most accurate descriptions of the cosmos. A constant so constant it resists explanation. And yet, no one knows what it is. Is it the energy of the quantum vacuum itself? The restless hum of virtual particles that blink in and out of existence? Or something deeper, an unseen field pervading all of space, an echo of an earlier universe, or a footprint left by dimensions we cannot reach? If the vacuum truly carries energy, then empty space is not empty at all. It is alive, a sea of fluctuations, fields, and ghostly whispers, everywhere and nowhere, shaping the evolution of the cosmos while remaining untouchable. But this vision of a living vacuum defies the tidy logic of physics. Why should it have precisely the value it does? Not infinite, not zero, but balanced at the razor's edge between chaos and collapse. If it were slightly stronger, galaxies could never form. If weaker, the universe might have fallen back upon itself. Instead, it floats, perfectly suspended in an impossible equilibrium. It is as though the universe were fine-tuned, not for life, but for mystery. In the laboratories and observatories of the modern world, this tension haunts every calculation. At CERN's Large Hadron Collider, protons crash together at near-light speeds in search of clues. The Higgs boson, the missing symmetry, the quantum origin of gravity. Yet the more discoveries unfold, the less the constants of nature seem explainable. Each revelation adds precision, but no closure. Each answer widens the void. Even Einstein's own equations appear almost prophetic, hinting that space-time itself may bend not only to matter, but to the pressure of the vacuum. In this picture, dark energy becomes a property of existence itself, the cost of being something instead of nothing. But that raises a darker question. Why should nothing have a cost? In the equations, the vacuum is the ground state, the lowest possible energy level. Yet even this nothing has structure, symmetry, and tension. It resists being truly empty, and when pushed too far, it may even collapse. A false vacuum, some theorists say, a fragile equilibrium that could, in principle, decay at any moment, rewriting the laws of physics in a single cosmic instant. If the vacuum we inhabit is not the ultimate one, then somewhere in the deep landscape of reality lies a truer form of nothing, one that would not sustain stars or life or meaning, and the day it arrives would be silent, instantaneous, complete. No warning could come, no signal could escape. The constants that define matter and time would dissolve, and the universe as known would simply stop being that universe. Though the probability is vanishingly small, the thought lingers, a phantom beneath the calculations, a reminder that even the most stable seeming reality may rest upon a mathematical knife's edge. The fabric of the cosmos, space-time itself, is therefore not a fixed stage, but a trembling lattice of probability and uncertainty. It expands, curves, and stretches, guided by laws that do not agree with one another. General relativity governs the cosmic symphony, while quantum mechanics plays its own dissonant rhythm. And in between those competing scores, existence somehow keeps time. It is this disunity that gives modern cosmology its quiet despair. Every triumph, every black hole image, every gravitational wave detection, every quantum experiment reveals not harmony, but contradiction. We can describe the universe exquisitely well, but cannot explain why those descriptions work. We can measure its age, its expansion, its composition, yet cannot tell why it exists in the form it does, nor why it allows itself to be measured at all. There are those who say that perhaps the problem is not in the equations, but in expectation, that perhaps the universe was never meant to add up in human terms, that logic and mathematics are local languages, tools evolved on one small planet, by one curious species, and that the cosmos may simply not care to be fluent in them. Others, more daring, suggest that what we call contradictions are not errors, but glimpses of a deeper symmetry, a higher dimensional order where relativity and quantum theory are not opposites, but shadows of a single unseen truth. A theory of everything, as it is sometimes called, though it may describe a universe that cannot be understood by beings who exist within it. In this sense, the failure to make the universe add up is not the end of science, but its most profound clue, because somewhere, between the infinities that diverge and the constants that refuse to explain themselves, lies a secret, one that speaks not of chaos, but of design hidden beyond comprehension. And so the question lingers, delicate as the thread that binds galaxies to gravity. Is the universe incoherent because we lack the language to read it, or because it was never written to be read? As physicists stare deeper into the equations, into the void between relativity and quantum truth, they are left not with answers, but with awe. The numbers no longer comfort, the constants no longer hold. The universe, in its elegance, its absurdity, its shimmering silence, remains both perfectly balanced and profoundly irrational. The fabric does not add up, and perhaps that is the point. Across the silent expanse of the observable universe, galaxies spin in quiet defiance of physics. Their outer stars, by every classical rule, should drift away, flung outward into the darkness by centrifugal force. Yet they do not. They cling to their spiraling arms as if held by invisible hands, bound by something unseen, something that outweighs everything visible. This hidden scaffolding, this ghostly glue, is known as dark matter. It does not shine, it does not reflect, it does not touch light in any way that human eyes, or even the most sensitive telescopes, can perceive. And yet, its gravity bends starlight, sculpts the skeleton of galaxies, and shapes the fate of the universe itself. The first hints came not from theory, but from observation, from the slow, careful patience of astronomers peering into the void. In the 1930s, Swiss astrophysicist Fritz Zwicky studied the Coma cluster, a swarm of galaxies drifting in deep space. What he found was disturbing. The galaxies were moving too fast. Their visible mass, the stars and gas and dust that could be measured, was nowhere near enough to keep the cluster bound. By Newton's law of gravity, it should have torn itself apart. Zwicky proposed a radical idea. There must be invisible mass, unseen matter providing the extra pull. He called it dunkle materie, dark matter. Few believed him. The claim seemed absurd, almost mystical. But decades later, the same anomaly appeared again, this time within individual galaxies themselves. In the 1970s, Vera Rubin and Kent Ford measured the rotational speeds of stars in the Andromeda galaxy. If Newton and Einstein were right, stars farther from the galactic center should orbit more slowly, just as planets in the outer solar system move slower than those near the sun. Instead, Rubin found that every star, near or far, moved with almost the same speed. It was as if an invisible halo of mass surrounded the galaxy, extending far beyond the glowing arms of stars. And that pattern repeated everywhere astronomers looked. Something immense and invisible was holding the cosmos together. Today, dark matter is believed to make up about 85% of all matter in the universe, yet not a single atom of it has ever been directly observed. The cosmos we can see, stars, planets, gas, dust, everything that burns or reflects light, is just a trace, a surface layer atop an unseen ocean. For half a century, Physicists have hunted for the source of that invisible gravity. They have built detectors deep beneath mountains and Arctic ice, sealed away from the noise of cosmic radiation. At Gran Sasso in Italy, the xenon experiment watches for the faintest glimmer of a dark particle colliding with liquid xenon atoms. In South Dakota, the Lux Zeppelin experiment listens for whispers from the abyss, the soft recoil of unseen matter brushing against reality. But the universe remains silent. Not one dark matter particle has been found. No collision, no spark, no trace. The detectors sit in darkness, waiting for a visitor that may never come. Physicists call their hypothetical quarry WIMPs, weakly interacting massive particles, relics of the Big Bang that should drift through galaxies like ghosts. For years, WIMPs were the leading candidates, their properties predicted by elegant extensions of known physics. But with each new experiment and every null result, that hope fades. The more precisely humanity looks, the more the shadows seem to retreat. Supersymmetry, a grand theory proposing that every known particle has a heavier twin, once promised to explain the mystery. These superpartners could have formed the dark matter that now shapes the cosmos. Yet despite decades of work and the monumental power of the Large Hadron Collider, not a single superpartner has appeared. Supersymmetry, once physics' most beautiful dream, now wavers between faith and failure. Other ideas rise to take its place. Some physicists propose sterile neutrinos, cousins of the ghostly particles that stream through Earth by the trillions every second. These sterile versions would interact even less, hidden from all forces but gravity itself. Others imagine axions, minuscule, weightless particles that could collectively form the invisible halos enveloping galaxies. But no telescope, no accelerator, no experiment has yet whispered confirmation. And so, the question deepens. What if dark matter is not a new particle at all? What if it is a sign that gravity, the oldest and most trusted law in science, is itself incomplete? Modified Newtonian dynamics, or MOND, dares to suggest this heresy. It argues that perhaps Newton's law of gravity breaks down at the cosmic scale, that in the vast, faint outskirts of galaxies, gravity acts differently than expected. Instead of unseen matter, the universe might obey unseen mathematics. For a time, MOND produced astonishingly accurate predictions of galactic motion without invoking dark matter. But it stumbled when confronted with the cosmic web, the large-scale structure of the universe mapped by satellites and surveys. The gravitational lensing of distant light, the ripples in the cosmic microwave background, the clustering of galaxies, all point not to a change in gravity, but to something real and massive lurking unseen. Even so, the idea refuses to die. For each theory that collapses, another rises from its shadow. Some now suggest that dark matter could be made not of particles, but of primordial black holes, ancient remnants from the universe's first moments. Tiny gravitational wells form from quantum fluctuations long before the first stars ignited. If true, the invisible scaffolding of galaxies could be built from the relics of creation itself. But evidence remains elusive. No gravitational microlensing survey, no LIGO detection, no cosmic echo has yet confirmed such a vision. And so, humanity drifts in the paradox of a universe that can be mapped in exquisite detail, yet still refuses to reveal its foundation. Gravitational lensing paints ghostly outlines, light from distant galaxies bent by unseen masses, tracing the contours of an invisible realm. Computer simulations of cosmic evolution, like those from NASA and the European Space Agency, show how this dark framework shaped the grand architecture of the cosmos. Filaments of invisible matter stretch across the universe like veins, connecting clusters of galaxies into an immense web. Without it, the universe would be formless, stars would never have gathered, galaxies would never have spun, and life itself would never have had a place to arise. And yet, what is it made of? If it is matter, why can it not be found? If it is not matter, why does it mimic the pull of gravity so precisely? Every experiment, every satellite, every collider seems to circle the same truth: that reality's scaffolding may be beyond the reach of matter itself. Some physicists now whisper that perhaps the dark universe is not a missing piece of physics, but a reflection of something deeper, a limitation of human perception. If consciousness, time, and matter are bound within the same cosmic code, then perhaps dark matter is not a thing, but a side effect of how that code is written. Quantum field theory describes the vacuum as a restless ocean of energy, virtual particles flickering in and out of being, unseen but measurable in their effects. Could dark matter be another layer of that same sea, a deeper stratum of existence whose ripples shape the visible universe from beneath? Or could it be something stranger still? A mirror cosmos overlapping our own, invisible but gravitationally entangled, forever out of phase with the light we see. Theories multiply, but understanding does not. The more science learns, the less the shadows obey. In the quiet halls of observatories, deep underground laboratories and orbiting telescopes, the same haunting truth repeats itself. Dark matter behaves as if it were real, but refuses to be caught. The Bullet Cluster, a collision of two galaxy clusters 3.8 billion light-years away, seems to prove its existence beyond doubt. When astronomers mapped the event, they found that the hot gas, the visible matter, had slowed from the collision, but the gravitational mass had passed through unimpeded. The invisible had separated from the visible. It was the first cosmic photograph of dark matter's presence. And yet, even that image explained nothing of what it truly is. Every answer, every clue, every triumph collapses back into silence, a silence that feels less like absence and more like refusal, as if the universe itself has chosen to keep one part of its body in shadow. Perhaps the dark universe is not a puzzle to be solved, but a veil drawn across a truth that consciousness was never meant to see. Maybe reality itself requires mystery, a boundary between what can be known and what must remain hidden. In that sense, dark matter is not merely a scientific problem, but a philosophical mirror, a reminder that even in an age of particle colliders and cosmic maps, humanity still lives surrounded by darkness, shaped by forces it can neither touch nor name. It is there, in the space between stars, in the curvature of galaxies, in the silent expansion of the void. It is the invisible hand that writes the geometry of existence, a presence that refuses to announce itself. And as telescopes stretch farther into the cosmic night, as detectors listen for whispers beneath mountains of stone, the question only grows more profound. Are we searching for matter, or for the edges of our own understanding? Perhaps the universe, in its infinite patience, will never answer. Perhaps the shadows that shouldn't exist do not hide something missing, but reveal what it means to look into the unknown, and realize that the unknown is looking back. In the vast quiet of space, everything seems orderly. Stars move in predictable arcs, galaxies spin like clockwork around their dark centers. Gravity reigns with solemn authority, curving space-time, shaping destinies, but beneath that calm surface, at scales smaller than imagination can stretch, the universe performs a different kind of dance, one that defies rhythm, logic, and even causality itself. At the quantum level, the laws of physics, the very structure of reason, begin to fracture here. Particles do not follow the rules of matter. They shimmer between existence and absence. They interfere with themselves, split, reunite, and collapse in the laboratory of the subatomic. Every certainty dissolves. When a single electron is fired through two slits, it should pass through one or the other, yet it passes through both until it is watched. When observed, it collapses into one possibility, as if reality itself waits for consciousness to decide what is real. This is not myth or metaphor, this is experiment. The quantum world has revealed truth so disquieting that even the most steadfast minds have trembled before them. Einstein, who curved space and slowed time, could not accept what the quantum proposed. God does not play dice, he said, but dice, it seems, are all the universe owns. The Copenhagen interpretation, born from the work of Niels Bohr and Werner Heisenberg, tells us that at the smallest scales, reality does not exist independently. It is only probabilities, waiting for observation to bring them into being. The act of measurement does not reveal the world, it creates it, and yet, something stranger still lurks beyond probability entanglement. The most unsettling phenomenon ever observed: when two particles interact, they become linked. Forever separate them by a centimeter or by a billion light years, and still their states remain connected. Measure one, and the other instantly responds. No signal travels between them, no wave, no particle, no vibration of space-time, just an instant correlation that should be impossible. Einstein called it spooky action at a distance. He was right to be unsettled. Because this quiet defiance of light speed limits, tears a hole in the very geometry of the cosmos. Experiments decades later proved the unthinkable. John Bell, in 1964, derived a theorem, a test if quantum mechanics were correct. Local realism must fail. And when physicists ran the experiments, Aspect in the 1980s, Zeilinger in the 1990s, and countless others since, local realism did fail. Reality is non-local information moves without a path. The cosmos, it seems, is not bound by space as we understand it. This is not the mechanical clockwork universe Newton imagined. This is something woven together, a single, instantaneous whole. Each particle, each fluctuation, each bit of energy knows the state of all others, as if space itself is only an illusion, a projection of deeper connection. But gravity refuses to obey in the quantum realm. Particles flicker, vanish, and return, creating a restless ocean of uncertainty. Gravity, however, moves like a glacier, smooth, continuous, classical. It curves space-time but never jitters. It bends light, but never blinks at the Planck scale, the unimaginably small threshold where both quantum and gravity should meet. The equations break down. The universe refuses to reveal what it is made of. Physicists have spent a century chasing the ghost of unification, the dream of a single theory that binds everything, from quarks to quasars. They call it the theory of everything. But perhaps everything is too much to ask. String theory once offered salvation. In its delicate mathematics, the universe was not made of points but of tiny vibrating strings. Each vibration created a particle. Each pattern a force, gravity, electromagnetism, the strong and weak nuclear forces. All could arise from one elegant framework, a cosmic symphony beneath the chaos. But the price of that beauty was dimension 10, then 11, hidden folds of space-time. Beyond human sense, worlds curled up so small they could never be observed. And though string theory predicted countless possible universes, a multiverse of almost infinite variety, it predicted nothing we could measure, no tests, no proof. Only mathematics stretching toward infinity-loop quantum gravity tried a different path. It imagined space-time itself not as a smooth fabric, but as a network of tiny loops, discrete grains. Like the pixels of reality, gravity would then emerge not from curvature, but from the quantum stitching of these loops, a geometry that vibrates at the Planck scale. It was a vision both humble and radical, but even here, contradictions multiplied. The equations worked, but not everywhere. Time lost meaning, space lost continuity. The deeper one looked, the less there was to find. At the heart of this betrayal lies a paradox older than humanity itself, that truth may not be one thing. The quantum refuses unity, it divides, it dissolves, it hides. And so, the universe might not be built upon certainty, but upon contradiction. Particles are waves. Observation creates matter. Information transcends distance. And gravity, that great keeper of order, cannot speak their language. What then is real? Some have turned to new ideas, where gravity is not a force at all, but an emergent property, a byproduct of information itself. Perhaps, they say, space-time arises from the entanglement of quantum bits. Space-time, as the geometry of information, Eric Verlinder's emergent gravity, the holographic principle, the ADS-CFT correspondence. These theories whisper a haunting thought that everything we see, touch, and inhabit might be a holographic shadow projected from a deeper quantum realm. In such a universe, there is no true separation between the small and the vast. Between here and there, every galaxy, every photon, every trembling atom might be encoded in a single cosmic equation, still waiting to be understood. But as the mathematics grows, so too does the distance from comprehension. Each new theory, elegant, intricate, precise, folds back upon itself, revealing more questions than it resolves. The quantum betrays not just our physics, but our philosophy, because if reality can exist and not exist, if cause can follow effect, if time itself can run both ways in the equations, then meaning becomes slippery. The human mind evolved to measure distance, to predict movement, to expect cause and consequence, is simply unfit for the scale of quantum truth in the dark laboratories beneath mountains. Detectors weight tons of xenon, germanium, and argon, shielded from the noise of cosmic rays. They listen for particles that may never come, for the faint whisper of dark matter, for the tremor of quantum gravity, and in the great accelerators, protons crash together with the force of stars. Yet every collision reveals the same pattern, a universe that hides its source code with deliberate silence. The betrayal deepens, for each discovery only multiplies the unknown at CERN. In the wake of the Higgs boson, hope burned briefly. Supersymmetry promised balance, a partner particle for every known one, restoring harmony to the quantum equations. It would explain dark matter, it would unite forces, it would close the gaps. But the detectors found none. No superpartners, no signs of the hidden symmetry that was supposed to rescue physics from its chaos, and so, another cathedral of theory crumbled. Perhaps the betrayal is not in nature, but in expectation. Perhaps reality was never meant to be unified. Maybe the universe is not a single song, but a discordant chorus, melodies that overlap, resonate, and sometimes cancel. A structure without foundation. A truth without center quantum mechanics may not describe what is. It may describe what can be. A language of possibilities, not of being and gravity, that patient curve of time, may belong to another sentence entirely. The closer we look, the less we see, the more precise our instruments, the more elusive the universe becomes. Reality recedes into abstraction, like a mirage retreating before the traveler. And yet, there is beauty in this betrayal, because it reminds us that knowledge is not conquest, it is wonder, a vast and trembling recognition that the world is far stranger than any mind can hold, so the quest continues. Physicists weave new fabrics of theory, quantum fields merge with geometric codes, black holes become laboratories for entanglement. Perhaps, they say, the secret lies at the event horizon, where gravity and quantum meet, where information burns, yet is never lost. Stephen Hawking once proposed that black holes destroy information. Later, he conceded they might not even hear. The cosmos plays its cruelest joke: information is conserved, but only if reality itself is rewritten. The betrayal, then, is not malicious. It is the price of asking questions too deep. At the smallest scales, the universe reveals not chaos, but complexity, not meaninglessness, but magnitude. Each failed theory, each unobserved particle, each broken symmetry is a reminder that understanding is not the same as control. The quantum betrays because it must, because truth, at its core, is not a straight line, but a wave function, not a command, but a probability. And in that soft uncertainty, the universe breathes, a cosmic laugh whispered across space-time, not mocking, but tender, not cruel, but infinite, because in the end, what humanity calls paradox, the cosmos calls harmony. In the deep silence between galaxies, something has gone wrong with the rhythm of expansion. For nearly a century, astronomers have believed that the universe has been stretching outward since the first light of creation, a silent exhalation of cosmic time. Yet the more carefully they measure that expansion, the more the universe seems to defy itself. Two answers now stand side by side, both drawn from precision and brilliance, and both impossible to reconcile. One tells of a young universe expanding faster than expected. The other describes a calm, older cosmos, whose pace is slower and steady. Both cannot be true, and yet both are. This contradiction has come to be known as the Hubble tension, a quiet war within cosmology, a conflict between the earliest light of the universe and the modern galaxies it left behind. It is not merely a matter of error or calibration, it is a fracture at the foundation of space and time themselves. The story begins, as so many cosmic riddles do, with Edwin Hubble, the man who first measured the universe's expansion in 1929. By observing the faint glow of distant galaxies, he discovered that the farther away they were, the faster they seemed to retreat. It was as if space itself was stretching, every point moving away from every other, not through motion, but through creation. This relationship became known as the Hubble constant, the cosmic rate of expansion, the pulse of the universe itself. For decades, astronomers refined its value, building telescopes that reached farther and deeper into the void. They expected convergence, precision sharpening into certainty. Instead, they found dissonance. The Planck satellite, launched by the European Space Agency in 2009, observed the cosmic microwave background, the faint afterglow of the Big Bang, frozen when the universe was only 380,000 years old. By analyzing the minute ripples in that radiation, scientists could infer the physics of the early cosmos, its density, composition, and rate of expansion. Their result was astonishingly precise. The universe, according to Planck, should be expanding today at about 67 kilometers per second per megaparsec. But elsewhere, the Hubble Space Telescope was watching the modern universe, measuring the distance to nearby galaxies using the flickering brilliance of Cepheid variables and the detonation of Type Ia supernovae. This approach, led by Adam Rees and the S80ES collaboration, yielded a different answer: 74 kilometers per second per megaparsec. A difference small on paper, yet enormous in implication, because no amount of improved calibration, no adjustment in data could make the two agree. If both measurements are right, then something fundamental, something buried deep within the nature of space itself, must be wrong. Physicists tried to explain it away. Perhaps dust distorted the ancient light. Perhaps the early universe's density had been miscalculated. Perhaps the stars used as markers flickered with hidden irregularities. But each hypothesis fell apart under scrutiny. The data was clean, the instruments unerring. The tension remained. In the calm chambers of observatories and research centers, a quiet panic began to spread. The Hubble constant was not a simple number anymore. It had become a mirror reflecting two incompatible realities. Some began to suspect the universe itself had changed. Perhaps the laws of physics were not as constant as once believed. Perhaps something had evolved between the early cosmos and now a field, a particle, an unseen form of energy altering the course of expansion. One theory invoked an elusive force called early dark energy, a transient form of pressure that briefly accelerated expansion after the Big Bang before fading into silence. Such a field could reconcile the two conflicting measurements, smoothing the tension between the cosmic past and present. But if true, it would mean that dark energy, the mysterious power driving cosmic acceleration today, has existed in more than one form, shifting its strength and behavior across time. A dynamic, living energy field woven through the very geometry of the universe. Others turn to the possibility of new neutrino physics, invisible particles that once carried momentum through the early cosmos, subtly influencing the expansion rate. If neutrinos had unknown interactions, or if entirely new species of them existed, they could change the universe's earliest rhythm. The problem was not in the data, it was in the underlying symphony of existence. Still others proposed something more radical. That space itself is not what it appears to be. The standard image of the cosmos, a smooth, stretching fabric, might be only a metaphor. In modern quantum gravity theories, space may not be a continuous sheet, but an emergent phenomenon, a vast web of information arising from deeper, microscopic rules. In this view, the distances between galaxies are not things that expand, but patterns of relationships, changing networks of quantum information. It is the holographic universe, an idea that suggests all of reality is encoded on a distant boundary, and what we perceive as depth, volume, and expansion is merely a projection. If this is true, then the concept of an expanding space could be an illusion, a byproduct of how information organizes itself. The Planck data, then, may be telling one truth about the holographic code, while the Hubble data reveals another, both valid within their domains, both incomplete, two reflections of a deeper, unseen geometry that refuses to flatten into understanding. And still the numbers do not settle. Every new telescope, from the Hubble to the James Webb, adds more precision, but no peace. Recent data from gravitational lensing and baryon acoustic oscillations has only deepened the divide. No experiment has found the missing thread. In an ordinary science, such uncertainty might suggest human error, But in cosmology, it suggests something stranger, that reality itself might not be uniform. Perhaps the universe is not expanding at a single rate everywhere. Perhaps the cosmos is not as homogeneous as Einstein's equations assume. If the distribution of matter and energy varies subtly across vast scales, then local and distant observations could reflect different cosmic clocks. In one region, galaxies race apart slightly faster. In another, slightly slower, a patchwork of expansion stitched by unseen variations in density or curvature. In that case, the Hubble tension would not be a mistake. It would be a message, a sign that the universe, like everything else in nature, is uneven and alive. The philosophical implications are unsettling. If space and time are not consistent across the cosmos, then the notion of universal law falters. What is constant in one epoch may not be in another. The idea that the cosmos obeys a single, timeless set of rules may be nothing more than a comforting myth. Einstein's equations still describe the local curvature of space-time, but perhaps that geometry is not fundamental. Perhaps the deeper reality is not made of space, but of relations, networks of quantum information that give rise to geometry only when observed at scale. In this picture, expansion is not the stretching of a physical medium, but the growth of informational complexity. Each new galaxy that drifts away is not moving through space, it is emerging from it. Space is not a container, it is the pattern itself. Even time begins to lose its meaning here. If expansion itself depends on perception, on how observers measure distance and light, then perhaps there is no single timeline to the universe's growth. Perhaps the cosmos does not expand in time, but creates time as it expands. Quantum cosmology hints at this possibility, that the very act of observation helps define the temporal structure of reality. In the timeless equations of Wheeler and DeWitt, the universe as a whole has no clock. It exists in a static superposition of all possible configurations, and what we call cosmic history is merely one path through that frozen landscape. If so, then the disagreement between the early and modern universe may not be a contradiction at all. It may be the shadow of a deeper truth, that time itself is not absolute, but emergent. That what we measure as expansion is simply the unfolding of information within a timeless whole. To scientists, this growing mystery feels like madness, the quiet unraveling of reason. Each new discovery, each elegant equation, leads not to clarity, but to contradiction. Two cosmic speeds, two versions of time, two incompatible truths, all coexisting within a universe that should, by all logic, be one. The Hubble tension is no longer a problem to be solved. It is a window into the limits of human understanding. It exposes the fragile boundary between measurement and meaning, between data and the invisible architecture behind it. Perhaps the universe does not expand into space at all. Perhaps space expands into us, into consciousness, into perception. And what we call distance is only the separation between what can be known and what forever escapes knowing. Across observatories, from the Atacama Desert to the frozen poles, telescopes still chase the expanding sky. They listen for the faint whisper of the cosmos in microwave and infrared light. They measure, recalibrate, refine, and each time the riddle deepens. The Hubble tension remains, unbroken, unyielding. It stands as a monument to a truth that humbles even the greatest minds, that the universe, in its quiet immensity, may not wish to be consistent. For all the power of human reason, for all the machinery of observation and mathematics, the cosmos continues to write its own contradictions, calmly, beautifully, indifferently. And somewhere beyond the reach of instruments and theory, beyond even imagination, the true expansion continues, not of space, but of mystery itself. There comes a moment in every age of discovery when observation reaches the limits of comprehension, when the instruments are sharpened beyond the edge of reason and the universe begins to whisper in contradictions. Call it the frontier, but it is more like a mirror, a surface where knowledge reflects upon itself and begins to fracture in this era. That mirror is the cosmos itself, dark energy, a term born not from understanding, but from surrender. It accounts for nearly 70% of the universe, yet it has never been measured, seen, or contained. It is the silent pressure that drives galaxies apart, stretching space-time, as if it were the breath of something vast and unseen. A force so gentle it can't be felt, so omnipresent it rewrites the future of the universe. And so, speculation takes the stage where evidence refuses to speak. Some imagine dark energy as the whisper of the multiverse, a faint pulse bleeding through from neighboring realities. In the mathematics of string theory, other universes are not fantasy. They are necessity, each defined by its own physical constants, its own balance of particles and forces. Our universe, then, might simply be one bubble among an infinite foam, expanding within a cosmic sea, where every fluctuation births a new beginning. If true, then the vacuum of our own cosmos, the so-called cosmological constant, may not be constant at all. It might be the gentle hum of existence itself, vibrating across hidden dimensions that our physics can only guess at. But there is a darker interpretation, one that views the vacuum not as stable ground, but as a cliff-edge physicists call it the false vacuum hypothesis. In this view, the universe sits in a temporary state of balance, metastable, not eternal like a ball resting in a shallow valley, stable only until the smallest quantum fluctuation knocks it over the ridge. If that happens, a new kind of vacuum would bloom outward at nearly the speed of light, rewriting the laws of physics as it goes. Every atom, every particle, every structure of matter would dissolve, not in heat or fire, but in silence. The end, if it comes, would arrive before the thought of it could form. And yet, this possibility is not despair, but symmetry. For it reminds us that even the universe may live on borrowed stability, and that permanence, perhaps, is the rarest illusion of all. Beyond these fears and fascinations, there is the deeper question of what space even means. Is it truly a fabric that stretches, or something that merely appears to do so when information rearranges itself? And in the holographic principle, a theory born from black hole physics, space and matter may be emergent. Every three-dimensional event could be encoded upon a distant two-dimensional boundary, just as a hologram projects depth from a flat surface. This idea, radical yet elegant, suggests that reality itself is a projection of quantum information. Not an illusion in the shallow sense, but a reconstruction, the universe decoding itself into perception. In this view, the cosmos is not built from particles, but from data. Every point in space, a bit of information. Every law of nature, a rule of compression. The boundaries between real and imagined, between fundamental and emergent, begin to dissolve, and with them, the comforting notion that the universe exists independently of observation. Others turn to gravity, that most ancient of mysteries, for answers that defy its own nature. What if gravity, rather than a force, is a side effect, an echo of thermodynamics, of entropy's endless drive to spread and equalize? In the work of physicist Eric Verlinde, gravity arises not from mass, pulling on mass, but from the information structure of the universe seeking balance. It is not something acting upon space, it is space itself responding to disorder. Such a view erases the boundary between physics and information theory, between the tangible and the conceptual, and yet in doing so, it may explain what has long been called dark matter. Perhaps the missing mass of galaxies is not matter at all, but the gravitational residue of information hidden in the cosmic fabric. Still others look outward, beyond the visible dimensions, toward higher realities, predicted by string theory. If our universe is a three-dimensional brain floating in a higher dimensional bulk, then gravity, unlike the other forces, might leak into those unseen dimensions, weakened here, but still immense beyond our view, an elegant possibility. And yet, experiments, from particle accelerators to satellite measurements, have found no trace of these extra dimensions. No resonance, no deviation, no echo of the unseen. The silence grows louder, and so, physics turns to the unthinkable, to the birth of time itself. Could time be an emergent property, not a fundamental ingredient? If entropy, the measure of disorder, defines direction, then perhaps time is only the universe's way of tracking its own decay. A statistical mirage born from the movement toward equilibrium. The equations of quantum mechanics and general relativity are, after all, time-symmetric. They work equally well forward or backward. Only observation breaks the symmetry. Only consciousness seems to remember one direction and not the other. In this view, time is not a river, but a reflection. It does not flow. It accumulates. Each moment a layer of probability solidified by perception. And beyond that perception, perhaps all moments coexist: birth, death, and everything between, a frozen landscape of space-time where motion is illusion and change is merely perspective. Einstein once said that the most incomprehensible thing about the universe is that it is comprehensible at all to him. The cosmic order was rational, an architecture of perfect logic waiting to be revealed. Stephen Hawking, gazing through the same abyss, called it the mind of God, a poetic surrender to the symmetry that seemed to govern all things. But what if the universe is neither rational nor divine? What if its structure is statistical chaos, a self-organizing storm of quantum probabilities, and consciousness, fragile, transient, wandering, is merely the temporary witness of its turbulence? In such a cosmos, meaning is not written into the laws of nature, it is written into the act of seeing them. The universe becomes aware not through divine will, but through us, through the eyes that measure it, the minds that model it, the curiosity that questions why it exists at all. Perhaps the search for ultimate theory, the equation of everything, is not a path toward clarity, but toward understanding our own limits, because every attempt to explain the impossible reveals something deeper about the observer. That logic, as powerful as it is, may not be the native language of reality, and yet science persists through the silence of the cosmic microwave background, through the flicker of distant supernovae, through the precision of gravitational wave detectors listening for ripples in the invisible. The theories continue to evolve: inflation, supersymmetry, holography, multiverse, each an instrument not of certainty, but of exploration, each daring to describe the indescribable, the impossible. After all, is not a wall, it is a mirror that shows how far curiosity will go before faith must take its place. And when that moment comes, when mathematics reaches the edge of language, all that remains is awe, the recognition that the universe may never be fully understood, that its strangeness is not a flaw in our science, but the reason science exists. For in the end, perhaps there are no final laws, no ultimate symmetries, no absolute truths hidden beneath the equations. Perhaps the universe is a story that tells itself endlessly, and the listeners, the observers, the thinkers, the dreamers, are simply the means by which it continues to be told. There was once a time when instruments served as extensions of certainty, when a telescope's lens or a collider's magnet seemed merely tools, obedient eyes and hands of reason. But now, they have begun to speak back, and what they say defies their makers, high above the dust of human doubt. The James Webb Space Telescope drifts in perfect stillness. Its mirrors gleam like petals of gold, tuned to catch light older than memory itself. When it first opened its gaze to the infant universe, astronomers expected a familiar pattern: small, chaotic galaxies just beginning to form. Instead, Webb found giants, massive galaxies, already ancient, standing only a few 100 million years after the Big Bang, too vast, too luminous, too evolved for the young cosmos that birthed them in images sent across 1 million miles of darkness. Stars burned where no stars should have been. The timelines cracked. The models trembled. If these galaxies are real, and evidence grows that they are, then the universe built structure far faster than theory allows. Gravity, star formation, dark matter, all would have to behave differently in those first moments, as if the cosmos itself had skipped a step in its own evolution. Some astronomers whisper of new physics, of primordial conditions unlike anything seen, since others suggest that our understanding of light and distance may be incomplete. That redshift, the measure of cosmic expansion, may hide more than it reveals, whatever the answer. The Webb telescope has not just observed the early universe, it has exposed a contradiction at the heart of cosmology itself, beneath the Earth, in caverns of steel and magnetism. Another instrument hums, the Large Hadron Collider, humanity's most powerful particle accelerator, spins protons near the speed of light, forcing them to collide in a storm of creation. It was here, in 2012, that the Higgs boson was found, the long-sought key to the standard model of particle physics. a triumph that completed the mathematical map of matter's known ingredients. But since then, the silence has been deafening. No supersymmetric particles, no dark matter candidates, no hints of extra dimensions. The universe, at the smallest scales, has refused to offer any surprises. And yet, that quiet is itself a paradox, because the standard model, for all its precision, cannot explain gravity, cannot describe dark energy, cannot predict the dominance of matter over antimatter. It is a map that ends mid-continent, beautiful, but incomplete. Each new collision, instead of expanding the frontier, deepens the mystery of why no frontier appears. The instruments work perfectly. The data are clean, but the universe itself seems to be withholding something. Perhaps the laws of physics, once thought eternal, are emergent. Perhaps they shift, evolve, or arise only within certain conditions. Or perhaps, more unsettling still, the framework through which we interpret the data is what requires revision in the cold clarity of space. Another observer joins the chorus, the Planck satellite, designed to read the faint afterglow of creation. The cosmic microwave background has mapped that relic light with exquisite precision. From its patterns of temperature and polarization, cosmologists have reconstructed the early universe with near perfection, but not complete perfection. In Planck's data, subtle anomalies appear. A hemispherical asymmetry, one side of the universe slightly different from the other. A mysterious cold spot, a vast region of sky where the microwave background dips below expectation. Statistically improbable, yet stubbornly persistent. These are not errors in measurement. They are fingerprints of something unaccounted for. Perhaps they are remnants of cosmic inflation, the brief, explosive expansion after the Big Bang, or the gravitational scars of other universes brushing against our own. Or perhaps they are the quiet signatures of physics not yet written. The cosmos, like a canvas, showing brushstrokes that do not match the painter's plan. Each anomaly whispers a quiet defiance that the universe, even at its origin, was never truly uniform. That symmetry, so long worshipped as the sign of perfection, may have never been real at all, across every scale. From the quantum to the cosmic, the instruments now speak in contradiction. The Large Hadron Collider finds nothing where something should be. The Planck mission finds something where nothing should be. The James Webb finds galaxies that should not yet exist. And neutrino detectors buried beneath Antarctic ice find particles that arrive from directions they should never come. Each machine, each measurement, expands precision. Yet every answer points toward unreasonly. Irony is quiet, but immense science was built upon the assumption that observation leads to understanding, that better instruments yield clearer truths. Now, those same instruments expose the fragility of that belief. They are not confirming physics anymore. They are dismantling it, piece by piece, with perfect accuracy in this strange new age. Data has outpaced theory. The equations lag behind the sensors. Human imagination trails the precision of its own machines' quantum computers, designed to simulate the fabric of probability, are beginning to reveal correlations that classical logic cannot describe. They do not break the laws of physics. They question what a law even means. For when computation itself begins to behave unpredictably, the boundary between science and philosophy blurs at Fermilab. The Muon G2 experiment measures the magnetic moment of a subatomic particle with exquisite precision, and finds that it does not match theory. A discrepancy so small, it should be negligible, yet if real, it hints at forces beyond the standard model, unseen particles or hidden symmetries that subtly warp reality. And at the South Pole, the IceCube Neutrino Observatory listens to ghostly particles passing through the Earth. Some arrive with energies that defy explanation, seemingly too powerful to be born from any known cosmic source. Even the high-energy jets of distant quasars cannot account for them. They are, in a literal sense, impossible, yet they exist. And so, the universe must adapt. It is as though nature has begun to turn its experiments back upon us, as if every advance in observation uncovers not a deeper layer of order, but a deeper layer of mystery. This is the betrayal of precision. The moment when science, in reaching for truth, finds that the truth is receding. The instruments question their makers not through rebellion, but through fidelity. They reveal, with absolute honesty, that the universe is not what we assumed it to be, that our methods, our lenses, equations and constants are themselves part of the mystery, not the key to it in this light. Even error becomes profound, because an anomaly is not a flaw. It is a signal, a reminder that certainty was always temporary. Some theorists whisper that perhaps the instruments are too perfect, that their measurements have reached a limit beyond which the concept of law loses meaning. Quantum indeterminacy, cosmic variance, and chaos. The universe may contain domains where predictability itself is an illusion, where observation no longer refines, but distorts, where reality, under sufficient scrutiny, becomes unmeasurable. If that is true, then the universe is not a puzzle to be solved. It is an ongoing computation, infinite, self-modifying, forever incomplete, and in this computation, humans and their instruments are not outside observers. They are subroutines, entangled participants in the code they attempt to read. There is a quiet beauty in this paradox, because every contradiction implies a deeper truth waiting to emerge. Every instrument that questions its maker is proof that understanding evolves. When Galileo lifted his crude telescope toward the sky, it did not confirm the heavens, it shattered them. When Einstein described gravity as geometry, he did not simplify physics, he rewrote it. Perhaps today's contradictions are the beginning of the next revolution, the web. Telescopes' ancient galaxies may one day reveal new physics of cosmic birth. The LHC's silence may conceal the pattern of a hidden symmetry we have yet to name. Planck's cold spots may become the first evidence of universes beyond our own. In that possibility lies both humility and wonder, for it means that even the act of questioning remains infinite in the end. The instruments do not betray humanity, they fulfill it. They remind a species born from dust that curiosity itself is sacred, that truth is not an endpoint, but a motion, a pulse running through time, from the first atom to the final star. And perhaps that is the real message behind their contradictions, that the universe, like the instruments that study it, was never designed to be fully understood, only witnessed. For in every question that unravels, in every discovery that destabilizes what came before, the cosmos continues to speak, not in answers but in echoes, and through those echoes, of light, of matter, of thought, the story continues endlessly, beautifully, and still, defiantly unknown. There is a silence in the deep sky that does not feel empty, a stillness between galaxies that seems to wait, as though listening, and across that silence, a question echoes, one that turns science upon itself. What if the universe is aware of being observed? At the smallest scales, where the rules of everyday reality collapse, physics encounters something that feels almost alive. Quantum mechanics, the language of the unseen, describes a world built not of solid things, but of probabilities. An electron exists in many places at once, until an observation forces it to choose. A photon travels every possible path, until a measurement declares just one. This is not speculation, it is experiment. The double-slit experiment, first performed over a century ago, continues to unsettle modern physics. When unobserved, particles behave like waves spreading through space, interfering with themselves, but when measured, when watched, they act as if they know. They collapse into singular points, obeying the logic of certainty only after an observer has entered the equation. The act of observation does not merely reveal reality, it participates in creating it. This is the quantum betrayal of objectivity, that reality at its core might be relational, that the cosmos may not exist in full without something or someone to experience it. John Archibald Wheeler, a student of Einstein and one of the great architects of modern physics, once proposed a daring thought, it from bit, that everything, matter, energy, even space-time itself, arises from information, that the universe is not built from particles, but from questions and answers. Each interaction, each observation, a yes or no exchange that crystallizes existence from possibility. In Wheeler's view, the cosmos is not a machine. It is a conversation. Every photon that has ever struck an eye or a detector, every atom that has been measured, every qubit that has collapsed, Each is part of this vast dialogue between the universe and itself, and in that dialogue, meaning is not an accident. It is structure modern physics has begun to find evidence of this informational foundation hidden deep within its equations. Black holes, once thought to erase everything they consume, now appear to encode their secrets on their surfaces. The Bekenstein-Hawking entropy formula revealed that a black hole's information is stored not within, but on the boundary that separates it from space. The holographic principle, born from this paradox, suggests that the entire universe may function in the same way. A three-dimensional world projected from two-dimensional information at its edge reality. In this picture is a hologram of pure data. What we see, touch, and measure is the shadow of an invisible computation. If true, then existence itself behaves as if it is aware of its own information, as though the universe is not indifferent, but self-referential, a system that contains the rules for observing itself in laboratories around the world. Experiments continue to probe this uneasy marriage between observer and observed at Delft University in 2015. Physicists performed one of the most rigorous tests of quantum entanglement ever conceived. Pairs of photons were generated and sent to detectors separated by hundreds of meters. Each time one photon was measured, the other instantly mirrored its state, faster than any signal could travel between them. It was as though distance itself had vanished. Einstein had called it spooky action at a distance and resisted its implications. But the data was clear. The universe does not behave like a stage upon which particles dance. It behaves like a network of correlations, where information connects everything, everywhere, all at once. To speak of here and there becomes meaningless. Observation does not occur within space-time. It helps define space-time. This idea has led some physicists and philosophers to a haunting possibility, that consciousness and cosmos are not separate phenomena, but reflections of one another. The participatory universe, Wheeler's final vision, suggests that observers are not late arrivals in a pre-written play. They are part of the script writing, that through the act of observation, through the steady gaze of awareness, the universe brings itself into being. In this sense, meaning and matter are intertwined. The cosmos does not simply exist to be understood. It exists through understanding at first. Such an idea seems to drift toward mysticism, but modern physics keeps returning to its doorstep. Theories of quantum information describe the universe as a computation unfolding in time. Quantum fields, the invisible ocean from which all particles emerge, behave as if governed by algorithms of probability. Entropy, once seen as mere disorder, is now understood as information lost or dispersed. Even the arrow of time, the one direction that seems absolute, may be nothing more than the flow of information toward complexity. Time, in this view, does not pre-exist experience. It arises from it. If no consciousness were present to perceive the unfolding of entropy, would time still flow, or would the universe remain suspended? A vast equation awaiting input. Astrophysicists studying the cosmic microwave background, the afterglow of the Big Bang, have found that the structure of the universe seems eerily optimized for observation. The fundamental constants of nature, the speed of light, the mass of the electron, the strength of gravity, exist within narrow ranges that permit complexity to arise. A slightly stronger gravity would have collapsed the cosmos. Too early, a slightly weaker electromagnetic force would have prevented atoms from forming. Stable bonds between these razor-thin margins, life and mind emerge. Some interpret this as coincidence. Others call it the anthropic principle. The simple truth that the universe must allow observers to exist, because observers exist to notice it. But the question lingers, is consciousness a consequence of cosmic tuning? Or is cosmic tuning a consequence of consciousness? If observation gives reality its final shape, then perhaps awareness is not a byproduct of the universe. Perhaps it is its purpose. The philosopher of physics Carlo Rovelli once wrote that information is the only thing that has meaning. In the realm of quantum gravity, where space-time dissolves into networks of relationships, it is information, not substance, that persists. From this view, the cosmos is less like a cathedral and more like a web-A structure woven from interactions, where every connection, every observation, adds to the pattern, and perhaps the pattern does not require understanding, only participation. The brain that wonders, the telescope that observes, the equation that seeks to describe, all are nodes within the same informational fabric through them. The universe experiences itself. Even the strangest frontiers of physics seem to mirror this idea. In quantum cosmology, some researchers suggest that the early universe may have existed as a superposition of many possible states, a wave function of entire realities. Only when observation, in any form, occurred did one branch become actual. The cosmos, then, could have collapsed into existence much as a particle does, born not from inevitability, but from interaction in this light. The Big Bang is not merely an explosion. It is an act of recognition. The universe did not begin as a mechanism. It began as a question and observation. Whether by atoms, photons, or minds, is its ongoing answer. Black holes, too, seem to play by these same informational rules. When a particle crosses their event horizon, it is never truly lost. Its quantum information remains encoded, written into the curvature of space-time, a cosmic memory, a ledger of existence that refuses erasure. In this way, even destruction becomes preservation, even silence becomes communication. If the universe keeps perfect record of its own unfolding, then it is not a void at all. It is awareness distributed through form, a memory made of light. Perhaps this is why the universe defies total comprehension. It was never meant to be solved. It was meant to be experienced. The equations fail not because they are wrong, but because they attempt to describe a system that includes the describer. The observer can never be separate from the observed to know. Reality completely would require stepping outside it, and that is something existence does not allow. The cosmos may, therefore, remain fundamentally paradoxical, not because it hides its truth, but because we are its truth, entangled in its self-reflection, in the quiet hum of the cosmic background, in the faint whisper of radiation left from creation's dawn. Something astonishing persists, a sense that the universe is not indifferent, that it participates, every star that burns, every particle that collapses, every mind that wonders. Each is part of a dialogue older than time. The cosmos speaks in photons, in gravity, in entropy, and listens in consciousness. One day, perhaps, physics will find the language to express this unity without surrendering to mysticism, a theory that binds information, observation, and existence into one seamless framework where mind and matter, far from being opposites, are revealed as reflections of a deeper principle. Until then, every telescope, every quantum detector, every thinking being remains a mirror, each reflecting the same question from a different angle. The question that began at the first spark of awareness and will end only when the last star fades. Who is observing whom? In the end, the universe may not know it is being watched. It may be watching through us, for when a conscious eye turns toward the night sky, when light, born billions of years ago, finally meets the gaze that can understand it, something profound happens. A circuit closes, information completes its loop, and the universe, in that brief shimmer of perception, becomes aware of itself. The story of existence, then, is not one of discovery, it is one of participation, a cosmic dream that can only continue so long as someone is there to dream it. And in that fragile act of observation, from the first mind that looked up at the stars to the last that will, the universe remembers what it has always been, a question made visible, a silence aware of being heard. The modern age of science was built on certainty. For 4 centuries, the equations of Newton and Einstein, the mathematics of order and motion, carried humanity across oceans of ignorance. They mapped the heavens, tamed electricity, split the atom, and stitched time and space into a single fabric of comprehension. It seemed for a brief and dazzling century that the universe could be fully known, that its logic would unfold like a grand equation, one elegant truth at the heart of all existence. But now, that dream flickers. The light of understanding has not gone out. It has scattered, refracted into paradox. At the frontier of discovery, the universe is no longer a solved riddle. It has become a whispering labyrinth, and science, once so confident, stands in quiet confession before the unknown. Physicists now admit that what they call reality may not even exist in the way we imagine. That space-time, the very stage upon which all matter moves, might not be fundamental at all. At its deepest levels, it could be emergent, a kind of mirage born from information. Like the shimmer of heat above a desert road, space-time could be a consequence, not a cause. The numbers tell a stranger story still. 95% of the cosmos, all its mass, all its energy, lies unseen. Dark matter outweighs the visible universe by a factor of 5. Dark energy, a nameless pressure driving galaxies apart, fills the remaining void. Together they form an invisible empire, dominating the cosmos, yet defying every instrument of human reason. When cosmologists speak of this unseen realm, their voices waver between wonder and disbelief. They can measure its pull, trace its influence, map its fingerprints in the cosmic microwave background, but they cannot touch it, cannot explain what it is. It does not absorb light, nor emit it, nor interact with the ordinary particles that make up stars, planets, and people. It is a cosmic ghost, and yet it rules everything. The deeper science looks, the more its instruments betray it. The James Webb Space Telescope, meant to confirm theories of cosmic evolution, instead found galaxies too ancient, too vast, too organized to exist so soon after the Big Bang. In the faint light of those primordial structures, the universe seems older than it should be, or stranger than the models allow. Every observation forces a new question. Every discovery unravels a law once thought unshakable. The Planck satellite, which mapped the relic radiation of the early universe, found something equally disquieting: a cold spot, a vast region of the cosmos inexplicably emptier than its surroundings. It may be an artifact of physics yet unknown, or perhaps, as some suggest, an imprint of another universe brushing against ours. The data itself does not say, it merely stares back, indifferent and infinite. Quantum mechanics, the theory of the very small, fares no better in the realm of certainty. It describes a world where particles flicker in and out of being, where probability replaces truth. Even after a century, its interpretation remains divided. Are particles real, or are they merely waves of potential, collapsing into form only when observed? Niels Bohr called it the end of causality. Einstein called it incomplete. And yet, every experiment ever made, from the double-slit interference to Bell's inequalities, confirms the quantum strangeness. Reality, it seems, refuses to obey the logic that birthed it. The Large Hadron Collider once promised to illuminate this darkness. It found the Higgs boson, the long-predicted cornerstone of the Standard Model. And then, silence. No supersymmetry, no new particles, no portal to a deeper layer of truth. The data is clean, too clean, almost mockingly so, as if the universe has hidden its deeper code behind an event horizon of comprehension. What remains then is not a universe that explains itself, but one that resists explanation. The equations of general relativity and quantum field theory, humanity's two greatest triumphs, cannot coexist. One describes gravity as the curvature of space-time. The other treats forces as exchanges of quantum particles. When combined, they dissolve into infinities, contradictions, and chaos. It is as though nature itself refuses to be unified, as if the laws that govern the very large and the very small speak in dialects the other cannot understand. String. Theory once offered a bridge, the promise of harmony through the vibration of infinitesimal strings across 11 hidden dimensions, but its beauty proved fragile. Each attempt to calculate reality's shape only multiplied the possibilities. There were not 1 or 10, but perhaps 10 quintillion possible universes, each with its own physics, its own constants, its own laws. If everything is possible, then nothing is inevitable. And physics, once the search for necessity, became the study of contingency, the poetry of chance. It is here that modern science turns inward, toward reflection. The cosmologist's blackboard now looks more like a confession than a calculation. The deeper the understanding, the more profound the mystery becomes. To know that 95% of existence is invisible, that space and time might be illusions, that the constants of nature may shift across the cosmos. This is no longer the triumph of knowledge. It is the humility of awakening. The philosopher of science might say this is not failure, but evolution. Science was never meant to end in certainty. Its purpose was to refine the questions, to strip away illusion until only the unknowable remains. For in the end, to understand everything would be to erase the wonder that compels understanding in the first place. Perhaps the universe is not an answer, but an invitation. Not a problem to solve, but a relationship to experience. Each new telescope, each collider, each quantum experiment is a conversation across eternity. The cosmos whispering back, sometimes in silence, sometimes in paradox. There are physicists now who dare to speak of consciousness itself as a player in the cosmic drama. If observation collapses the wave function, then perhaps awareness and existence are intertwined. Information, not matter, not energy, may be the true essence of being. In John Wheeler's words, it from bit, reality from information. Existence is computation, a universe that encodes itself by being observed. This is no longer the clockwork cosmos of Newton, nor the smooth continuum of Einstein. It is something more fluid, more participatory, a universe aware not in mind but in motion, where entropy births time, where information shapes form, where the act of knowing helps define what is known. It is possible even that the universe exists because it can be known, that consciousness is not a passenger but a partner in the act of creation. The observer and the observed, forever entangled in a cosmic feedback loop of meaning. And so modern science, having climbed the mountain of understanding, finds itself looking into a mirror. Its instruments reach to the edges of time. Its equations dance at the Planck scale. And yet, the reflection stares back, silent and unsolved. It reveals not mastery but mystery, not conquest, but communion. When Einstein said that the most incomprehensible thing about the universe is that it is comprehensible, he touched upon this paradox, that order and chaos are twin aspects of the same truth. When Hawking spoke of the mind of God, he spoke not of divinity, but of pattern, of coherence amid the infinite. And now, the physicists of today stand between those echoes, neither claiming knowledge nor abandoning wonder. They have learned, at last, to say the words that science once feared most. We do not know. The confession of modern science is not one of defeat, but of reverence. The cosmos, vast and patient, has revealed only enough for curiosity to survive. Its remaining secrets, dark energy, quantum gravity, the nature of consciousness, are not barriers but horizons. They invite exploration, not resolution. For perhaps the truest law of the universe is that it will never be fully known, that every act of discovery will birth new shadows. That wonder, not certainty, is the final constant. In the quiet halls of observatories and the deep tunnels of particle colliders, amid the flicker of screens and the hum of magnetic rings, science whispers to itself, not in equations, but in awe. It has seen the structure of atoms and the afterglow of creation. Yet what it finds most mysterious is that it can see at all. The confession is simple and infinite. The universe owes us no clarity, but still it shines. And still we look. It begins, as it always does, with a question, and it ends, as it must, with silence. Between those two, humanity has lived its entire story, reaching outward through centuries, through lenses and equations, through the dust of dead stars and the hum of quantum fields. Each discovery, each fragment of knowledge has brought the illusion of closure, yet every answer reveals a deeper fracture, another veil drawn over the next horizon. Perhaps that is not failure, perhaps it is design. From the falling apple to the orbit of planets, Newton once believed he had glimpsed the mind of order, a clockwork universe governed by laws both precise and eternal. But the centuries that followed broke that symmetry. Einstein bent time, quantum theory shattered causality, and the cosmic web revealed a universe not built of certainty, but of chance. The dream of understanding gave way to something far more delicate. The awareness that comprehension may itself be fleeting, an emergent spark within the darkness. The universe, vast and indifferent, does not speak in the language of meaning. It simply is, and yet, through consciousness, it wonders about itself. Physicists once thought that ultimate truth would be written in the language of mathematics, a single equation elegant enough to bind gravity and light, matter and mind. But the deeper the mathematics became, the further it drifted from the tangible, strings vibrating across hidden dimensions, quantum loops that weave space-time from uncertainty, equations that describe universes that may never exist. It is as if the cosmos resists translation. Each attempt to define it disturbs it, like ripples in a still pond. The closer one looks, the more the image dissolves. And so the dream of certainty transforms into something humbler, more human, the quiet awe of not knowing. The universe offers no clear narrative. Galaxies are born, shine, and collapse into nothing. Stars burn themselves to ash to make the elements of life. Planets arise from chaos, orbit for eons, then vanish in silence. Even consciousness, that most intimate spark, may be temporary, a chemical flicker on a cooling rock. And yet, within that flicker, the cosmos learns to see itself. A pattern of atoms arranged in such improbable symmetry that thought emerges, asking why. It is not the answer that matters. It is the asking, for the act of wondering is itself a form of creation, a mirror the universe holds to its own mystery. Meaning then may not be discovered but invented, not found in the structure of the cosmos, but born in the fragile awareness that contemplates it. There are scientists who now suspect that reality itself may not be fundamental, that everything, space, time, energy, could emerge from the flow of information. The universe, they say, may be a computation, a self-reflecting algorithm. Each quantum interaction, each entangled state, could be a bit of code in a cosmic simulation of existence. But if that is true, who or what is the observer? Who runs the code? Or perhaps there is no outside observer at all. Perhaps reality is self-aware through the very process of perception. Consciousness as the universe folding inward upon itself. Meaning, in this view, is not built into the fabric of space, but arises from the collision between knowing and not knowing. It is the fragile balance between information and imagination, between truth and mystery. The cosmic microwave background still whispers its ancient song, the faint afterglow of the Big Bang, stretched thin across 13.8 billion years. In its pattern of temperature and light lies the earliest record of creation. But even there, in the purest data the universe offers, anomalies persist. Cold spots where order fails, asymmetries where none should exist. Hints, perhaps, that our understanding is a shadow of something larger, a reality that refuses to be fully seen. Dark matter still drifts unseen between galaxies, shaping everything while revealing nothing. Dark energy still drives expansion faster and faster into the unknown. The laws of physics still contradict themselves at the edge of a black hole, where gravity and quantum theory collide in mathematical war. And through it all, humanity continues to look upward, not to conquer mystery, but to live within it. If the universe truly has no meaning, then it has given meaning to everything that asks for it. Every equation written, every telescope launched, every midnight spent tracing starlight across the void. All of it is meaning made manifest by the act of pursuit. The paradox is exquisite. A meaningless universe gives birth to beings desperate for meaning. An indifferent cosmos produces life that feels wonder, beauty, grief, and love. Out of entropy comes awareness. Out of chaos, curiosity. Out of silence, the sound of thought. This is not an accident. It is the essence of being, that in the vastness of what cannot be known, consciousness blooms as the one phenomenon that seeks to know. Einstein once wrote that the most beautiful experience is the mysterious, the fundamental emotion that stands at the cradle of true, art and true science alike. Perhaps that is all the universe ever offered, beauty without explanation. To exist within it is to participate in something boundless, to be both observer and observed. When the James Webb Space Telescope stares into the past and sees galaxies forming before time should allow, it is not chaos-defying reason. It is the cosmos reminding itself that logic was always an invention of limited minds. When the quantum vacuum flickers with particles that appear from nothing, it is not magic. It is existence reminding itself that nothingness has never truly existed. The absurdity of it all, the scale, the silence, the persistence, is its beauty. One might imagine that someday humanity will stop searching, that telescopes will darken and equations will find closure. But the history of discovery suggests otherwise. For every mystery solved, two are born. The universe does not shrink with knowledge. It expands, not in distance, but in depth. Each insight peels back another layer of wonder, revealing not an answer, but another question. To live as a conscious being, then, is to accept the infinite loop, to chase meaning through a landscape that offers none, and in doing so, to create it. It is to love the question more than the certainty, to find grace not in resolution, but in the reaching. Perhaps that is what the universe intended all along. if intention can exist in something so vast. Not that we understand it, but that we try. Not that we conquer the dark, but that we light small candles within it. Meaninglessness in that light is not despair. It is freedom. It is the open field in which curiosity runs unbound. It is the silence from which every question is born. And in that silence, between the flicker of galaxies and the hum of atoms, between the birth of a star and the blink of an eye, something extraordinary happens. Awareness awakens. The cosmos begins to know itself. The story of science does not end with knowledge. It ends with wonder, the same wonder that began it. From the apple's fall to the whisper of quantum foam, from the polished mirrors of Webb to the void beyond the last star, the search itself is the meaning, the confusion, the contradiction, the awe. All of it is the heartbeat of a universe alive with questions. For if the cosmos makes no sense, it mirrors its own creators perfectly. Sentient chaos trying to understand itself. The mystery remains unsolved but alive. And somewhere, in that trembling uncertainty, lies the pulse of creation. Final cinematic closing for narration and visual fade. In the end, the universe does not need to explain itself. It only needs to exist, radiant, impossible, and endlessly becoming. Meaning is not hidden in the stars. It is written in the gaze that seeks them. And as long as there are eyes to look up and minds to wonder why, the story continues. Not as an answer, but as the most beautiful question ever asked.